We're going to do a little bit more about zeros of polynomials. So last time I was telling you what the zeros were. So we need to be able to have a way to kind of guess what those zeros are supposed to be. So we're going to do something called the rational zero theorem. So when we talk about rational zeros, we're talking about rational numbers. So, oops, second. It came unplugged. So when we talk about rational zeros, we are talking about numbers like 2/3, because rationals are going to be a quotient of integers. So it could be negative numbers as well. And it can be whole numbers because we can also write a whole number as a quotient of integers. So we're looking for numbers like this. So either they're going to be fractions or they're going to be integers. So we want to find zeros of a polynomial function using rational zeros theorem. And after we do the rational zeros theorem, most of what we're going to be doing is very similar to what we were doing in our last section. There we go. So we have a polynomial. Oh, this is just our generic polynomial. Has integer, if the polynomial has integer coefficients, meaning an minus 1, a2, a1, a0 are rational numbers. Oh, integer numbers, sorry. So remember, integers are like this set of numbers. So you're -3, -2, -1, 0, 1, 2, 3, etc. So you don't have to worry about this one so much right now because for everything we're going to give you is going to have integer coefficients, but in the future, this has to be integer coefficients. Then P divided by Q, where P and Q is reduced to lowest terms, is a zero of F when P is a factor of the constant term, A is A naught, and Q is a factor of the leading term, AN. So what we're saying is that we want to have P, Q. These are my potential zeros. Because it might be it's not going to work at all, but these are potential zeros of fx. And we know that P over Q is going to be factors of the constant term over factors of your leading term. Let me go back here a second. I thought I put it in here, but I didn't. So a way to think about this is that when you're trying to figure out your PQ, think the silly snake put his tail over his head. If you think of this, you can think of this as like a snake. Let me make a better snake there. Here's we'll start here. This is where I want my head to be. This is my head. This is my tail. So what we're thinking is that my snake is doing this. So this is my A naught over my AN. So factors of A naught over AN. So just to help you remember, because you're going to want to switch this when you're doing this. Alrighty. We're going to list all possible rational zeros of x is equal to 4x to the fifth plus 12x to the fourth minus x minus 3. And we want to decide which of those possible zeros are going to be real zeros. We know how to do this because we had that remainder theorem. So what we're going to have is P over Q. These are my, like I said, possible rational zeros. P is going to be factors of A naught, which is my -3. Q is going to be factors of AN, my leading coefficient. So what we're going to have here is that my factors, so we have positive factors and negative factors because -3 is not only divisible by 1, but it's also divisible by -1. So we'd have plus or minus 1 are factors of 3 and another factor plus or minus 3. Those are the numbers I can divide into -3 and do it evenly. So for 4, we'll have plus or minus 1 because 4 is divisible by 1. 4 is also divisible by 2, and 4 is also divisible by 4. So those are my possible factors. So those are my factors. So my possible zeros. So we have 1 over 1. And that could be positive or negative because if it's positive 1 over positive 1, then it's positive. If it's -1 over positive 1, then it's going to be negative. If it's -1 over positive 1, it's going to be negative again. If they're both negative, it will be positive. Whatever that's going to be, 1 over 1, which we know is going to be 1, is going to be positive or negative. Then we have, because this is on top, right? 1 over 2. Then 1 over 4. So we keep them positive and negative because it could be a positive 0 or a negative 0. Then we move on to the 3's and we put the 3's over all of my possible or possible denominators. So we'll have plus or minus 3 over 1, plus or minus 3 over 2, and plus or minus 3 over 4. So if you want to make this a little easier, my possible zeros are going to be, we'll write this in red. Everything we need to check. Plus or minus 1, plus or minus 1/2, plus or minus 1/4, plus or minus 3, plus or minus 3/2, and plus or minus 3/4. Okay, so we want to know which zeros are going to be zeros, meaning that I need to go through, and this is where it gets a little time consuming, so I'm going to give you a way to do this a little better. But I simply just want to figure out what is f of -1 equal to? What is f of +1 equal to? What is f of -1/2 equal to? What's f of +1/2 equal to? So I want to do this for all my possible zeros. And as you see, I have 1, 2, 3, 4, 5, 6. If we double that, 12 possible zeros. So a way that we can do this is I'm going to use Desmos to help you kind of get through this part a little quicker. You can do this with an 84 as well. So I'll show you both. Desmos.com /backslash calculator. So we have f of x is equal to 4 x to the 5th. So we just type in our polynomial with 12 x to the 4th minus x minus 3. So from here, if I hit edit list, let me go back for a second. So I'm going to go here, edit list, and then I go to this create table. From here, it's telling me my x's and my fx's. Oh, I just put in my -1, my +1, my -1/2, my +1/2, my -1/4, my +1/4, my -3, my +3, my -3/2, my +3/2, my -3/4, and my +3/4. So if we start from the top, we see that neither of these, let me get a different color here. So this doesn't equal 0. So remember, if this equals 0, we have a 0. I'll write this over here. So -1 is not, we don't get a 0. So by remainder theorem, we're not getting a 0 here until we get to -3. -3 happens to be a 0. And then we see the rest of them also do not give us zeros. So even though it's a fifth degree polynomial, we only have one rational 0. Now that doesn't mean that the other zeros cannot be found. What it means is this. X equals -3 is a rational 0. Of x. And that x plus 3 is a factor. Now, there's zeros, they're just not going to be rational zeros. So the remaining zeros can be real, irrational, or they could be complex numbers. But they're not going to be rational. There could be remaining zeros. All I'm finding is possible rational zeros. So if you go and you look here, we do see that we do have a 0 here as well, and a 0 here. So we have two irrational zeros, and then we have a rational 0. Then we would have two more zeros that they're going to be complex zeros. Yeah. We're not going to worry about that right now. Let me do this with a TI-84. All right, if you're going to use the TI-84, you're going to want to go to y equals. And then in here, you're going to type in your polynomial. Oh, sorry, there's all the adds are popping up here. 4x to the 5th plus 12x to the 4th. Oops. And I said I'm having 84 and not an 83. Move over. There we go. Plus 12x to the 4th. Move out of the exponent. Negative x, -3. So if I go to second graph, oops, that's a graph. But if I go to second graph, that brings up to table. Now, notice I can't change anything. If that is going on, you need to go to second window that takes you to table set, and you need to turn independent to ask. Leave this one as auto. Then go to second table again and notice everything's missing. Then we can start entering in second table. The -1. Remember, this is for your negative, the +1. We know the 3 works, so we won't put everything in here. You put it in, you're going to see the same thing. So if you have an 84, you can do this as well on the 84. All right, so you're going to do a similar thing. Now your polynomial is g, which is 8x to the 4th plus 2x cubed minus 21x squared minus 7x plus 3. And you want to find all your possible rational zeros and determine which ones are actual zeros for the function. All right, so possible rational zeros. You are going to look at factors of 3, so your constant over factors of 8, which is your leading coefficient. So those possible factors would be for 3, plus or minus 1, plus or minus 3. Factors of 8 are plus or minus 1, 2, 4, and 8. So make a list over here. So my possible zeros. We can have plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4, plus or minus 1 over 8, plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 3 over 4, and plus or minus 3 over 8. So I could have minus 1, 1, minus 1 half, positive 1 half, minus 4, positive, or minus 1 fourth, positive 1 fourth, minus 1 eighth, positive 1 eighth, minus 3, positive 3, minus 3 halves, positive 3 halves, negative 3 fourths, positive 3 fourths, negative 3 eighths, or positive 3 eighths. Right, so we've entered in the polynomial. Let's get our table. So let's start typing our zeros. We got negative 1, 1, so neither of those seem to work. Negative 1 half, positive 1 half. Neither of those seem to work. Oh, let me see, negative 1 fourth, positive 1 fourth. Ah, we got one that works. So we have, let me get a different color for that. We got a 0 right there. So let's keep on going. We can do negative 1 eighth. We can do 1 eighth. We can do negative 3 and 3. Negative 3 halves. We do have to check all of them, 3 halves. We do have another one here. Which one? Oh, negative 3 halves. Then we move on to negative 3 fourths. 3 fourths. Where we got negative 3 eighths and positive 3 eighths. So we look here, that's where 2 of those zeros are, the 1 fourth and the negative 1 fifth. The other ones are going to be irrational numbers, but we only have 2 rational roots. All right, so we have another theorem. So if a polynomial equation is of degree n, then counting multiple roots separately, the equation has n complex roots. So these complex roots, they could be rational, irrational, which are both real roots, or they're going to be complex numbers. So if you remember, real numbers are also complex numbers. So when we say complex roots, we just mean that there's going to be n roots, and it's a combination of real and complex numbers. So AF plus BI is a root of a polynomial equation with a real coefficient. Then the imaginary number A minus BI is also a root. So the other part of this says that if A plus BI is a root, then A minus BI is also a root. as long as b does exist, because if that b is not is some is 0, then we're dealing with real numbers. So basically we're saying that imaginary roots exist in conjugate pairs. So if I have 4, or sorry, x to the fourth minus 6x cubed plus 21x squared minus 30x plus 3 equals 0. I want to find all of my roots. So we're going to have to find rational roots first if we can. Let's see if we can get this down to a quadratic. Once we get this down to a quadratic, we can completely factor. Okay. So let's look for our possible zeros. So we need factors of 13 and factors of 1. So this is going to be pretty easy. So we're going to end up with, we either can have plus or minus 1 on top, or plus or minus 13, because those are the only factors of 13, and my only factors of 1 are plus or minus 1. So my possible zeros are going to be plus or minus 1 over 1, or plus or minus 13 over 1, meaning it's just going to be plus or minus 1 or 13. Okay. If you take your calculator and you figure out like f of minus 1, that'll get me this into my calculator. So you could just type in each one of these separately if you wanted to, like I said, into Desmos. But let me get you these zeros, which ones are real zeros here quickly. Okay. I made a mistake when I tried to build this. So let me go back and change this. This should be x to the fourth minus 14x cubed. Let me bring that back. Plus 6x squared plus 89x minus 91. Sorry, I built the polynomial forward, but yeah, made a mistake there. So if we use this as my polynomial, same zeros because essentially, because we're just going to get a plus or minus. Let me go back here. So 91 is divided by 13. So the other ones we have are a plus or minus 7. So we end up with plus or minus 7 here. But if we go back and we check them all, yeah, sorry about that. Thought I had it all right. And then I went back and realized that I expanded wrong. So -1, it's going to be -6, 9. So that's not a 0. If we do f of 1, though, that's going to be a 0. So we know 1, 0. F of -7. Oops. Sorry, something happened there. -7 is going to be equal to 6,720, so that doesn't work. So if we just do just plain 7, it's not any better. We get a negative 1,512. If I do f of -13, oops, -13, that one is going to be another huge number. And then f of 13 is going to be 0 again. So these are my 2 zeros. So this is my polynomial and I have 2 rational zeros. And x equals 1 and x equals 13. So now once we have that, we can go back and we can start factoring this whole polynomial and solving it. So we're solving it means we want to find all the zeros. Okay. So these are my zeros, meaning that I have two factors I think I have. Bring that back. I lost my writing tool. Means that we think we have a factor that's x minus 1 and a factor that is x minus 13. So we're going to divide by the x minus 1 first. That means that I'm just using that 1, dividing that 0 out. And my coefficients here are 1 minus 14, 6, 98, and minus 91. If I bring down the 1 times 1 is 1. Negative 14 plus 1 is negative 13. Negative 13 times 1 is negative 13. 6, negative 13 leaves me negative 7. Negative 7 times 1 is going to leave me with a 91. 91 times 91 is going to leave me with 91, which gives me a 0. Which means that I have factored my polynomial here to x minus 1 times remainder coefficient x, x2, x3. So we get x3 minus 13x squared minus 7x plus 91. So that's my first factor. Now I'm going to take this, and so my other factor was minus 13, and divide by x minus 13. I'm just taking basically what is my my quotient here, and I'm dividing this out, because if this is a divisor of this polynomial here, it will be the divisor of this part right here. So we're using the 13. Well, we're taking out that 0 at 13. And now we have a remainder or a coefficient of 1, negative 13, negative 7, and 91. We drop the 1. 1 and 13 is 13. We get a 0. 0 and 13 is 0. So we get a negative 7. And I'm going to double check this, but I'm pretty sure that negative 7 and 13 are in fact negative 91. So this is my other remainder. So now I factored into x minus 1. I factored in x minus 13 from this part, meaning that factors into x squared minus 7, because this is my constant, my x, and my x squared. Okay. So now that we're at this part, let me make a little space for us here. All right, so we're looking at this. We had x to the fourth minus 14x cubed plus 6x squared plus 98x minus 91. That equals 0 and 1 to solve. And now we can say, well, we have x minus 1 times x minus 13 times x squared minus 7 equals 0. My choices are x minus 1 equals 0, x minus 13 equals 0, or x squared minus 7 equals 0. So we're going to put that all in the first line. So we have a little left to look at here. So here we see that x would have to equal 1. Here we see x would have to equal 13. And here, well, if we do x squared is equal to 7, then x has to be plus or minus 7. So my zeros are going to be at 1, 13. Well, actually, if I put them in order, it's going to be negative, I forgot my square root here, negative square root of 7, 1, positive square root of 7, and 13. Okay, so I'm going to ask you to try a few new things here. So in this case, we already looked for our rational zeros. So our rational zeros were, put these down again, negative 3/2 and a positive 1/4. So what we have here is factors that look like this. Okay, so we'll work our way through this one. But you have those zeros, so we're going to try factoring this, but you're going to factor with some fractions. So take a moment, try it on your own, and then we'll come back and we'll do it. Okay, so we're going to start with dividing by. Oops, sorry, let's move to the other screen. Sorry, you can't see what moved. There. We're going to start with this first factor here. So we're going to divide by 3/2. And we have 8 to -21, -7, and 3. So we're going to drop that 8 first. So 8 times 3/2 is going to be 12. 12 times 2 is 14. 14 times 3/2 is going to be 21. So we get a 0 here. Then we're going to be left with the 3/2. So let me get this here just a second. Some of you may have caught it. I made a typo. What is my 0? It is -3/2. Right, opposite sign of our factor. So I used a positive. Okay, let's do that again. So bring down the 8. 8 times this will be negative. See 2, -12. So we're going to be left with -10. 10 times -3/2 is going to give us positive 15. So that's going to give us a -6. -6 times -3/2 is going to be 3 a positive 9, leaving us with a 2. So 2 times -3/2 is going to leave us with a -3, so we get a remainder of 0. All right, so you're not getting a remainder of 0. You know these are supposed to be zeros, as I saw what's happening here. That's a hint that we're dividing by the wrong number. But what we're left with is that this is broken down into x plus 3/2, and then we have 8 x to the third minus 10x squared minus 6x plus 2. And now we're going to divide this by our other factor, so our x minus 1/4. So that means we're going to have a positive 1/4, what we're using, and we have 8, -10, -6, and 2. I drop down the 8. 8 times 1/4, well, that's going to be easy. That's 2. So -10 minus, or -10 plus 2 is going to leave me with a -8. -8 and 1/4 is going to leave me with a -4. Two. Oh, wait, that's not right. -2, leaving us with another -8. -8, and this is going to leave me with -2, which gives me my 0. So we factor this even further into 3/2 x minus 1/4, and then we have 8x squared minus 8x minus 8, and this is all supposed to be equals 0. So we want to factor this, so everything's got an 8, so we can pull out the 8, and we're left with x squared minus x minus 1. So we're just trying to find the zeros, right? We're not saying we're trying to factor in completely. We're going to use quadratic formula. So we have x is going to be negative b. So my b is going to be this -1. So it's going to be +1. Make sure I get these right. Then we're going to have plus or minus b squared. So a is 1, b is -1, e is -1. B squared is just going to be -1 squared minus 4 times a, which is 1, and c, which is -1, all divided by 2a. So we got 1 plus or minus. Let me see, this is going to be 1 plus 4. So this is going to be 5 over 2. So we are going to get two numbers. Square root of 5. So if we do this, 1 minus square root of 5 over 2 is going to be approximately negative 0.618. And then the other 0 would be approximately, with the plus, 1.618. So you could say that your zeros, or your solutions, because that's all we want is the solutions, right? So we had two solutions here, because we had those rationals, and then we got our other two, which are going to be irrationals. My solutions if I have 8x to the fourth plus 2x cubed minus 21x squared minus 7x plus 3 equals 0, those solutions are going to be minus 3/2, 1/4, and if you want to keep it real numbers, if you want to keep it as exact solutions that look like this, or you can say it's going to be negative 3/2, negative 0.618, 1/4, and then the 1/4, and then the 1.618. And these are my approximate solutions. And these would be my exact solutions. Right, so if fx is a polynomial of degree n where n is greater than or equal to 1, then the equation fx equals 0 has at least one complex root. So remember, by a complex root, this could be real or imaginary numbers involved. So it could be your complex root could be 3, or your complex root could be 2 plus 3i. It could look like either one. But what we're saying here is essentially is everything should have at least a root. So even going further, when you have a polynomial where n is greater than 1, so it's a it's a polynomial that's bigger than, say, x plus 2 or something like that. So it's got a bigger degree than 1. Then c, which you see is in my factored form here, the c's are complex numbers, possibly real, but not necessarily distinct. In words, an nth degree polynomial can be expressed as a product of non-zero, constant, and n linear factors, where each linear factor has a leading coefficient of 1. So we're able to write it so it's going to look like it always has a number out front and then a product of linear factors. So we're going to go back here a second. So we know this one, this part here, we said we pulled up the 8. So this can be written as 8 times x plus 3/2, x minus 1/4, and x squared minus x minus 1. So we want to write it as everything is a linear factor. So we know that the zeros that we had here were 1 plus or minus the square root of 5 over 2. So remember, this comes from a zero of -3/2. This had a fact, this zero was -3/2, and here the zero was +1/4. So the factor and the zero have a different sign. So we're going to write this as 8x plus 3/2, x minus 1/4, and we would have x minus 1 minus square root of 5 over 2, and minus 1 plus square root of 5 over 2. Just because we're just going to say here that the zero is positive, therefore the factor, we have to turn it into a negative. So I have taken this, and this is a linearization. So I've written this as a product of several linear factors. By that means they're all of degree 1. So most are going to use the linear